All right, welcome back, folks. So in the last section, we talked a bit about figuring out whether data are normally distributed. If you have normally distributed data, we can then take and use our sample data to determine estimates of population values. And so this week in this chapter, in chapter 7, we're going to talk about ways to estimate values for populations given their mean or whether we're given proportions. And we're also going to do that whether or not we know the population standard deviation, or whether we know the population standard deviation, or in the next section, if we don't know the population standard deviation. The process is very different in these first two it's very similar in these first two sections, with only very small differences. And so you'll see that as we go along. Okay, so we're going to talk about how to find confidence intervals, what they mean, how to find the margin of error, and then how to figure out the minimum sample size. What's the smallest sample size we need to determine the answer to some question, if we know the margin of error that we want. Recall that a population parameter is a value that represents a measurement for the entire population. Okay, so if we want to measure the average or the mean height of all community college students, right? So in this case, we're talking about every college student, community college student that that goes to college. Okay, there's going to be one unique value for that. Okay, when we measure that one value, we call that a parameter, right? That would mean we'd have to measure everybody. That's remarkably impossible. If we were to talk about that average height though, that one value, we'd use this mu symbol to represent that population value. Right? This is the population parameter. It's the population mean. Okay, now we couldn't measure every single community college student, right? But how could we determine the average height? Well, there's lots of different ways. You could go and just measure people. You could measure people as they enrolled, or you could just ask a few people, what's your height? Which is essentially kind of what we did in the survey, and you'll see some more of that later. But the idea here is that we have to use a sample in order to represent all of the community college students, because we can't possibly measure everyone. And so we can use that sample to then generate an estimate. Okay, we can really never measure every single person. So because we can't really measure everybody, we can estimate those parameters by measuring a sample, measuring statistics from samples. And so to estimate the average height, we would just collect a random sample, as random of a sample as we can get. And then we could calculate the mean of that sample. Okay, and the mean of the sample is represented by X with a line over it, right? X, sometimes called X bar. Okay, it is the mean of our sample. Now, will the average height of our sample be exactly equal to the average height of all of the students? Right? If we calculated that population parameter, would it be exactly equal to it? And the answer is going to be clearly, I would hope, no. Right? The answer that you get depends on the sample that you collect. Okay? There is only one population parameter. There's one single unique value that represents the average height of everybody, every community college student. Okay? But to find that one single unique value, you'd have to measure every single person, okay? Or have a value to represent every single person in some kind of way, either by asking them or measuring them. Okay? But you're going to get any number of sample means depending on which sample you collect, because there's hundreds, thousands of samples you could collect of community college students, and every single mean will be different. So how do you know, if you make an estimate from a sample, that you have a good estimate for that value? Okay, and one way that we can know that is what's called the margin of error. Okay, we can calculate a value that represents boundaries of where we'd expect to find most of our values. If some of this feels a little familiar to you, it's because last week and the week before in your Excel projects with the sample mean and the sample proportions, this is essentially what I had you doing. You've got all the pieces that you need to understand what a confidence interval is. The only thing I didn't do was directly name it. Okay, and now the calculations will look a little different, but in in the overall understanding of things, you were doing the same thing, which you'll see. So let's talk about the margin of error. Okay, that gives us an idea of how good our estimate is. Okay, no sample's ever gonna give us the exact population parameter, but we can take our sample and determine a margin of error. All right, get an idea of where we'd expect to find that population parameter based on our sample. It depends on the sample size, and it depends on the standard deviation. The more people you sample, the closer you are to that population parameter, right? The smaller the margin of error. Right? The margin of error goes down if you sample more people because you're more likely to have you've sampled most of the population or more and more of the population. If the standard deviation, however, kind of works the opposite way. If the standard deviation goes up, right, well, then your data vary more. More variance in the data mean a greater margin of error. Less variance in the data means a smaller margin of error. A smaller margin of error implies you're closer to the population parameter. A larger one implies your estimate's probably further away. And it's going to be a much larger range. And so again, you've had these pieces in a way, right? The margin of error is calculated from the population standard deviation and the sample size and what's considered a critical z-value. And this is chosen based on what we call a confidence level. And the confidence level is just how confident do we want to be in our estimate. Right? Now, you'll see this, how this represents or relates to the normal distribution in just a minute. Okay, but I did include this table here because it is somewhat helpful as a reference so that you don't have to go look it up every single time. But these are the critical values for Z. Okay, the critical values for Z you can put in a table. The ones in the next section are not as easy. Well, there's a table, but it's much more complicated. So the critical Z value, sometimes you see it written as Z with a star over it. You guys might see it as Z alpha over 2. I just refer to it as the critical value. Okay, but it is the boundary of our confidence level. Okay, so if we want to be 90% confident in something, okay, it's essentially the boundary of our normal distribution, which would mean we'd have 5% over here and 5% over here. And that would leave 90% in the middle. Okay, and so if our sample mean is in the middle, then we can be 90% sure that the population value is probably in between whatever these two values are, which is exactly what you did in your assignment last time. Now, I don't know if it was exactly 90%, okay, but I just had you do it in a slightly different way. And so we're just going to talk about how to do this in it's really a little bit easier this way. So here we have information about height along with the mean, standard deviation, and the sample size, and the critical value for a 95% confidence interval. Right, so let's find the margin of error given what we have here. Okay, the margin of error, you go and look here. Okay, it is the critical value times the standard deviation divided by the square root of the sample size. And so it's 1.96 times the standard deviation, which in this case is 2.5, the population standard deviation, divided by the square root of 18, or the square root of the sample size. So put that into a calculator. 1.96 times 2.5 divided by the square root of 18. We get a margin of error of 1.15. In this case, we're talking about height, so 1.15 inches. Now, how do we use that margin of error to find a confidence interval? Well, that's very, very simple. Confidence interval is just a range of values that represents the range where we can be reasonably confident to find that population parameter. Right? We can be reasonably confident that the population value is within this range. Okay? We can never use the exact sample mean and say that the sample mean is what the population value is. Right? We can only use a confidence interval and say that we could be 95% confident that it falls within these two values. Okay, it's determined using the estimate of the population parameter, right? So when you're dealing with means, the sample mean, X bar, and the margin of error, which I'll write as an E here. Okay, so if we want to find the confidence interval, it's just the sample mean plus or minus the margin of error. And so if we go back just briefly, our sample mean here, 65.53, we'll call it. X bar, 65.53. Okay, and then we have margin of error That was 1.15. So to find our lower boundary, we subtract 65.53 minus 1.15. That gives us 64.38, in this case inches. 65.53 plus 1.15, that'll then give us the upper boundary. Whoops, 66.68. If we add the two. And so we can be 95% confident, based on our sample, that the average height falls within those two values. This is the best that we can do with the estimate, right? We can't use the value directly in the middle, right? And that's why it kind of gets left out sometimes of the confidence interval itself, because the value in the middle is not really that important. That's just our sample measurement, right? What we're looking for is the confidence interval, where we expect to find all the values. So let's try another example, and here you can see what we're doing with the distribution. But again, this is kind of what you did before. IQ test is given to a simple random sample of 75 students at a certain college. The mean of that sample, 105.2. Okay, our sample size is 75. Scores on the test are known to have a standard deviation of 10. We want to construct a 90% confidence interval. Okay, so what we want is there to be 90% in the middle, 5% on each side. And so we can use this 90% value here, or you can use this value here. Either one is fine. We can find the margin of error as the critical value of z, 1.65, we'll say, times the standard deviation divided by the square root of the sample size. So 1.65 times 10 divided by the square root of 75. That gives us a margin of error of 1.91, or in this case, we'll just call it 1.9. And so then to find the confidence interval, we're going to add 1.9 to 105.2. And we're going to subtract 1.9 from 105.2, 107.1, and then if we subtract one, if I hit the right buttons in the calculator, 103.3. So we can be 90% sure, or 90% confident, that the values will fall within 103.3, the values for the IQ score, and 107.1. And so hopefully this seems like a little bit of an easier way to do what you did in your projects before, but it is essentially the same thing that you were doing. Okay, but it is, in my opinion, I think it's a little easier. The lifetime of certain type of battery is going to be normally distributed with a standard deviation of 20 hours. We have a sample of 50 batteries with a mean lifetime of 120.1 hours. And we want to construct a 95% confidence interval, okay, and then write an interpretation. And so again, we have a mean of 120.1 hours, standard deviation of 20 hours, and a sample size of 50. We want to find the margin of error, which is for a 95% confidence interval. We want the margin of error to be, the critical z value to be 1.96 times the standard deviation divided by the square root of the sample size. And so 1.96 times 20 divided by the square root of 50, and you should get 5.54 as your margin of error. To then find the confidence interval, we just add and subtract that from our sample mean. So plus margin of error 120.1 plus 5.54, 120.1 minus 5.54. And what you should get, 125.6, we'll just round to one decimal place. Now, 114.6. And so we can be 95% confident that the true value of the battery life of this particular battery is going to fall between 114.6 hours and 125.6 hours. So one thing that we want to look at too is we want to be able to compare different confidence intervals, right? So if we use this different confidence level for the same data, okay, let's just kind of see what happens. We have a random sample of 40 employees with a mean salary of $62,500, and the standard deviation is 34,100. Okay, the best point estimate, the best estimate we have for the true mean value is our sample mean, right? So 62,500. If we want to find a 95% confidence interval, and well, that's going to be, we're just going to put a 95 with it, right? That's 1.96 times the standard deviation, 34,100, divided by the square root of 40 for the sample size. And you're going to see we're going to do a very similar calculation again in just a second. And here we get 10, it's a bigger number, 10,560, we'll just round it to whole numbers, 568. And so for a 95% confidence interval, 62,500 minus 10,568, 51,932. For the upper value, we just add them. 10,568, 73,068. So now let's find the 99% confidence interval. We go and look at our table, that's going to be a critical value of 2.58. So 2.58 times again 34,100 divided by the square root of 40. We're just calculating the margin of error for a different confidence level. We get 13,911, we'll call it 10.5. Out to 11. And now just subtract and add 62,500 minus 13,911, 48,589. And then when we add the two, 76,411. So notice that the 99% confidence interval is larger, right? Because as we add to the confidence level, right, as we increase how confident we want to be in our answer, right, our sample is going to get wider and wider, or our confidence interval is going to get wider and wider, because we only have a sample of the data. And if we had a much larger sample size, that would shrink this down some. But just in general, if you add to the confidence level, then you add to the size of the margin of error. Increasing the confidence level increases the margin of error, right? That makes sure that the true population value is within the boundaries. Okay, and so it's going to increase the width of the confidence interval. Okay? If you're using the same sample, the higher the confidence level, the wider the confidence interval as those go up. So in some cases, you might want to determine an estimate and know the margin of error, right? So we're going to calculate the margin of error first. We want to calculate this estimate within half an inch or an inch. Okay? And so to do that, we can then calculate the sample size we would need for that margin of error, right? If we know the standard deviation of the population. Okay? So we can use this formula to calculate the sample size. And just make sure you round up, because if you get 96.04, right, then 96 alone won't be enough. You'll need 97 people. And so let's look at some examples of this before we move on to the other, to what happens when we don't know the population standard deviation. An IQ test is designed to have scores with a standard deviation of 15. A simple random sample of students is given in test in order to construct a 98% confidence interval for the mean IQ score. how many students do we have to test so that the margin of error will be equal to 3 points? And so let's go back just real quick and look at the formula. Okay. N equals the critical value of Z times the standard deviation divided by the margin of error squared. In this case, our critical value for a 98% confidence interval, 2.33. Our standard deviation is 15. And we want a margin of error within 3 points. And so to figure out the sample size we need here, 2.33 times 15 divided by 3, that's 11.65 squared, which is 135.7. So we need a sample size of 136 people. And that will get the margin of error less than or equal to 3 points. Let's look at one more example of this. A machine used to fill beverage cans. To put exactly 12 ounces in the can, the population standard deviation is given here. Okay. Again, we're going to want to find the sample size here. We're going to collect a random sample and have their volumes measured. We want a 95% confidence interval for the mean. How many cans do we have to sample for that the mean or for that the margin of error to be within 0.01 of an ounce? So we're testing to see if the machine is spitting out 12 ounces of beverage in each can. We're going to sample a whole bunch of cans and figure out and do a sample enough so that our margin of error is within 0.01 of an ounce. And so to do that, we want a 95% confidence level, confidence interval, 1.96. Our standard deviation of 0.05. And we want a margin of error of 0.01. And then we're just going to square that value here. 1.96 times 0.05 divided by 0.01. That's going to give us 9.8 squared, which should be close to 100. 96.04. So we'll have to sample about 97 cans. In the next section, we're going to talk about how to solve very similar problems, except when we don't know the population standard deviation. In that case, we just change our estimate a little bit, but we can no longer use Z values. We have to switch to using a different value. And we'll talk about that a bit at the beginning of the next section. Please let me know if you have any questions.